Right. Having studied the kinetic theory of gases and the properties of an ideal gas and some of the gas laws, now time to apply the knowledge to a given situation. And in the situation is this: a vertical hollow cylinder of height 1.52 meter is fitted with a movable piston of negligible mass. The lower half of the portion of the cylinder contains an ideal gas, and the upper half is filled with mercury. And the cylinder is initially at 300 Kelvin. Okay, so that means I have this initial situation like this. Let us say I have a cylinder, and say this is the piston of negligible mass. In this part we have gas, by G gas, and it is at 300 Kelvin. The vertical cylinder is of height 1.52 meters, so this height is 1.52 meter, and if I call this as h, this height is h by 2, and this height so also will be h by 2. The lower portion of the cylinder contains an ideal gas. This is the ideal gas. In the lower portion, lower half portion, it is specified, therefore we have taken half over here, and the upper half is filled with mercury. So this particular part, this part is filled with mercury, right, which we can probably show with some other color. So this is filled with mercury. The green part is filled with mercury. When the temperature is raised, half of the mercury comes out of the cylinder. Now what we do is we give this heat, so this gas expands. When this gas expands, the piston moves up and mercury comes out. And it is said that when the temperature is raised, half of the mercury comes out of the cylinder. And in that situation, we have to find out the temperature of this gas. Find the temperature of the gas, assuming thermal expansion of mercury is negligible. So the second situation, after we have heated it up, is something like this. Now the piston has come somewhere over here. This is the piston, this is the gas now. Half the mercury goes up. That means now this part, which is mercury, which again I'll show with green color. Mercury is only in this particular part. So it is said that half of the mercury comes out. So this particular length would h, it was earlier h by 2, now it will become h by 4, and therefore this will become h minus h by 4, h minus h by 4. Of course this height is h is equal to 1.52 meter, and now we have to find out the temperature over here of the gas. So what we'll do is we have this gas in two different states. So we will use the equation of state P1 V1. We'll use the equation P1 V1 upon T1 is equal to P2 V2 upon T2. So let us get these states. The initial state, that means in this particular condition, the temperature T1 is 300 Kelvin is given to us. What is the volume? Now volume is height into area. So let us assume the cross-sectional area to be A of the cylinder. So if cross-sectional area is A, then the height of the cylinder in the first case, of course we have initial condition, we are looking at the gas, right, and the final condition of gas. So height is h by 2, and if the cross-sectional area is, let us say, A, so volume V1 will be h by 2 into A. And what about pressure? The pressure acting on this gas is the atmospheric pressure P plus pressure generated by this height of the mercury column. So P atmosphere plus height of this mercury column. The height of this mercury column is h by 2 of Hg. So this will give me P atmosphere, which is 0.76 meter of Hg plus h by 2. H is 1.52. 1.5 divided by 2, 1.5 by 2 divided by 2 meter of Hg is equal to 0.76 meter of Hg plus 0.76 meter of Hg. So that means this pressure will be 2 times the atmospheric pressure. So I can write this as 2 times P atmospheric pressure. 2 multiplied by P atmospheric pressure. So this is P1. So I have obtained P1, V1, T1 for the initial position. Let us do a similar thing for the final position. T2 is to be found out. We don't know the temperature. This is T2. Volume V2. Now how much does the volume change? This has become H minus H by 4. So 3H by 4. The height is 3 by H by 4, and area of course will remain same, cross section area of the piston. Right? Okay, what about P2? Now P2 will be atmospheric pressure plus pressure of this much of column. So it will be P atmosphere, which is 0.76 meter of Hg plus H by 4. H by 4 of Hg is equal to 0.76 meter of Hg plus H is 1.52 by 4 of Hg. This will be 0.76 meter of Hg, which is atmospheric pressure, plus this is this will give me a value of 0.38 meter of Hg. So this is atmospheric pressure, P atmosphere, plus this is P atmosphere by 2, because 0.76 divided by 2 is 0.38. So this will give me 3 by 2 times P atmosphere. I hope you got this. This is 0.38, which is 0.76 by 2. So this is P atmosphere by 2. Adding these two will get 3 by 2 P atmosphere. Now we have got P1 V1 T and P2 V2 T2, and now we can use equation of state. So P1 V1 upon T1 is equal to P2 V2 upon T2. Therefore P1 is 2 into P atmosphere, V1 is H by 2 into A, H by 2 into A, and T1 is 300, is equal to P2 is 3 by 2 into P atmosphere, V2 is 3 upon 4 H into A, and multiplied by T2, which we want to find out. So a lot of things will get cancelled out of this. P atmosphere HA will get constant, P atmosphere HA gets constant, cancelled out. 2 gets cancelled out over here. So what do I have over here? Therefore I will have over here 2 upon 300 is equal to 3 is a 9 upon 4 T2. Therefore T2 will be equal to 9 by 8 into 300. 300 comes over here, T2 comes over here, 2 comes over here, so 4 to the 8, and 9 by 8 into 300. What does that give me? I'm going to quickly do that calculation. 9 multiplied by 300 divided by 8 equal to 337. 337.5 Kelvin T2. So this is how we can find out the temperature now in this condition based on the changes in pressure and volume. And this is an application of the equation of state. So if you know out of these 6 parameters, if you know 5, you will be able to find out the 6th parameter. So this is how we have used equation of state. In the coming up videos, we will be looking at other gas laws and see how they get applied in situations like this. Thank you.